Okay, so first of all, thank you for the introduction and thank you for inviting me to give a talk. So my talk is very applied. So I mean, as you can see in the middle of my talk, so I'm very the practical guy. So in terms of talk, so also I'm dealing with like the very like common problem in statistics. So trying to like the testing the mean vector in high dimensional data. So now if we move to these slides. So if we trying to recall the symposium today, so if I still remember, it's called, I trying to like memorize just like a few minutes ago. So it's called Big Data Challenges for Predictive Modeling of Complex Data, complex systems. And then I realized, and in my talks, so I include many keywords like the big data challenges for like the complex systems. So we know like these days, so we have many like the high dimensional data, and they have like the many applications. So I also like had a look in terms of the this symposium, and in the main introduction, if you check the last sentence, so we will say trying to find the application of the big data in by physical, chemical, biological science, and engineering. And in addition to like the mentioned in the symposium, so like if you check, so we can also have like the high dimensional data or even like the big data in like computational biology, like the econ and many other areas. Okay, so and in my previous like the research, so we know like the many statistical methods. So they are actually in terms of the methodologies, they are, I mean, general. So we suppose they can apply to this area, can apply to that areas. But for my previous research, so I mainly applied to the, in the previous 10 years, so to the gene expression microarray, and now these days in the next generation sequencing. So just in case, because we see like not like all of us, so we are like working in the bioinformatics. So I briefly like introduce what something called like the cDNA, like the microarray. So if I just like use some like a sentence to explain, like use like this well-known like the picture. So we assume if we have like trying to like compare to study like a certain tumor. So then as a comparison, so we usually look for like a group of like normal people as comparison and the patients with tumor. So then we apply like a certain like the RT-PCR technology to like enlarge the RNAs, and then like after we extract the RNA for the same number of copies, so we like labeled with different dyes, say like the dye for green and the dye 5, dye 3 for the red. And then we try to like combine the total amount of the RNAs. And we apply certain like a molecular, like the printer, and scan to certain like the chip. So here we can like assume here it's like a first gene, second gene, third gene, and fourth gene. So they are ordered, and we can figure them out in terms of which gene. And then we imagine if like for certain genes there's no relation with the tumor. So if in like the normal people and in patients, if they are constantly expressed, then in terms of the number of copies, so they are about the same. And we know like the same amount of the green and the same amount of the red, if we combine, they will come up with something called yellow. In that way, if we see some like the spot with like the yellow color, so we will say like they are constantly expressed. But in case if in like the patient like tumor guys, if like for a certain gene, like a first gene, if like it's like the overexpressed, then here we will have like the many more like the red like RNAs, and if we combine them, the red one will dominate the green one. And then in terms of the combined to printer, and you will see like the red spot. And the same idea, if like the tumors, they are like the underexpressed, then we will very few like the red ones and eventually turn out to the green ones. So like if we are like in the gene level, like for microarray, it's the idea behind it's actually very simple. So we try to find some like spots, they are like the significantly like the overexpressed with red and underexpressed with green, right? So that's like the very. And if we can see like in terms of publication, even like the yesterday, I hope to like update like slides, but I like check the Google like imaging, so I did not find like something like the new one like the 2018. So I still like follow this one. But we can see like the in terms of the number of publication from the microarray and the RNA. So like the now like the publication of the second the next generation sequencing like is much more in terms of total numbers. So now if we, after we have some brief introduction to like the cDNA microarray, so if we back to like a very classical statistical question, so we can, now let's assume if we later that P it's the number of the genes and it's the number of the samples, say like either like if two sample study, so like the number of the normal people and the patients. So in in practice, the number of genes are usually very large. So we are talking about thousands, tens of thousands. And in terms of the number of the samples, so there are many reasons we are not able to like get the same number as the dimension. So that's a problem. I mean, you can say like due to the budget, due to the availability of the patients, or due to the, many other reasons. And we know like now this kind of study we call it like the large P small n. So many challenge. And in the first talk, like Professor like also mentioned like in terms of the data structure. So we are all in the large P small n category. And now assume if we are interested in the class comparison. So we know, like as I just mentioned earlier, if like to detect the differential expressed genes. So if we want to see like the red and the green ones, so then we for each gene we run one test. So then we have like for many genes we have many one-dimensional like the hyper-testing. So in that way, in very classical statistics, we call multiple testing. But then like this is about like we starting from like the 2000. The first paper like in this one, it's like a Tiejun, their paper in 2001. So then like about like the 10 years later, close to like 2010. Then like the people like in particular like on the biologists, they are not very satisfied with the result from statistician. They feel the genes they will not like the function individually. So certain genes, so they will form like a gene set, and another name like we call like a pathway. So then like they hope to see like whether in addition to like each like individual genes, whether like the whole pathway, the whole gene set, they are going to be significant and they have certain functions. So I like again like yesterday I trying to like slightly update my slides. So I checked online and very lucky I find something can illustrate like what I'm trying to introduce. So I find like in 2000 paper. So in this one, and it's very clear. In terms of the multiple testing, if I check back for these slides, multiple testing, so then we are in the like the gene level analysis. For each gene, based on like the upregulated or like downregulated like in terms of the different color, and for each gene we have a test. That's we result in the like the multiple testing, and a very useful technique. It's called FDR control. And then like in the recent like 8 to 10 years, so people like the more interested in the gene set in terms of the like in terms of the pathway level analysis. Then we try to test in terms of like the pathway in normal and the pathway in like patients. So whether they are like has certain function and have some like the global like the connection with the tumor like the function. Okay, so Now, like given like we're talking about like for the gene set, so then we like look back in statistics. We know like the very early and the most famous like the test. So we known as the Hotelling test, T-square test, and the aim. I mean, if like here it's like just a scalar, one dimension, then we will go to either like a t-test, or if we square, we will run into the f-test. But in the mean vector case, so then the Hotelling test, in terms we have this test statistic, and we all know. So now these days, given like for the sample covariance matrix, I mean, given like on the large p small n, so this is like the singular, not invertible. So we have like the problem here. So the day like I start, I also like trying to like work something in this area. So it's like about like 2012. So during that time, so I just have like the new PhD student like coming in. So I ask as like the first project. So we check like the certain like literature and find even like though like the microarray like first introduced in 1995 and another paper in 1996. So I mean after like the 15 or close to 20 years, I mean there are still like many studies with a sample size quite small. So as I mentioned, like in the very beginning, say I'm very practical guy. I'm personally not interested in like not very interested in like the studies with like the p goes to infinity and n in a certain way, say like a log p, or another situation again goes to infinity. I'm more interested in situation. I mean all the time the sample size is small. So I will focus like my study on the high dimensional but like the small sample size study. So, and we know like no matter in which situation, so now the sample covariance matrix, it's going to be like the singular and it does not work if we say, so that's like the classical Hotelling has some problem. So then what's the approach in the literature? So in the literature, so the first idea, so given if the sample covariance matrix, I mean it's a singular, and we need to find a certain way to overcome the limitation. So what we can do, the easiest way, we will say, hey, let's just remove it. If we check back the slides here, so we need to like estimate this one. And really like the first approach. So like and if we date back this way for the like high dimensional testing, so we actually like date back to like one paper in Seneca. But I mean, of course, during the main focus on this one is not trying to dealing with the microarray. But but it's a very famous paper. So later on, like so there are like the many other papers. So that's the first approach. They are trying to like completely remove the sample covariance matrix from the test statistics. But there's another approach. But we can have situations say, hey, I mean p go to infinity, n go to infinity, and in that situation, people feel like we really like trying to find a way to estimate the sample covariance matrix. So we can try like some ridge type, shrinkage type, and trying to get the whole information back, make it invertible, and starting from here. So they are again like mainly like the different ways. So when we trying to like summarize the literature during that time, so we also like find there's like the third approach. So the third approach, it's a compromise between the first one and the second one. If we look into the first one, they even like removed the variance part. So we even, did not scale it. And here we're trying to like catch like all the information. But imagine if the dimension is 1,000 and if your sample size is less than 10. So you are dealing with a matrix with 1,000 times another 1,000. So there's like 1 million entries. But you only have information less than 10. How can you estimate, very accurate? In that situation, so it turned out, so even if you have found like the weight trying to dominate the diagonal case, so more weights to make more invertible. But it turned out, most information in the sample covariance matrix, they are just noise. And if you include like a huge noise inside here, so then eventually, there's no signal, noise ratio. So we feel like the third one might be like provide like a good compromise between this one. So we do not try to, estimate the covariance part, but we still trying to catch on the diagonal information on variance. And once again, they are different approaches. So then, that's our motivation. So as I mentioned, like not trying interesting like n go to infinity. And at least within this window, so we run certain simulation, and we do find the third category provide.
Can I ask a question about the diagonal comparison method? If we use the diagonal approach, would that just kind of implicitly assume that they are independent? What's the point of doing a kind of
like in the later, I will talk about this issue. This is like the diagonal covariance matrix. It's just the motivation. We trying to to derive the test statistic. So when we have the test statistics, if we trying to establish the null distribution, so we even for this one, so you very naively, if we assume totally remove. But once we trying to establish the null distribution from the here, so we still trying to catch upon the dependent structure. This is only.
It seems like the diagonal, basically you are doing this on each of the genes in the same pathway, and kind of do a sort of like the mean square divided by variance, and then adds up all the genes in the same pathway together. You're not taking into account the correlations at all.
No, from this point of view, actually, you can see probably 5 to 10 slides. You can see it, and then I will explain the details. Okay, yeah. How much time I still have?
15 minutes.
15 minutes. Good, great. Okay. So. And even based on some theoretical work, so we in statistics there are some the well-known papers. So they're talking about in situation for correlation if they are not very noisy. So we better to to not estimate them at all. Okay, so now this is the slides. So if we're talking about, as we mentioned, on the pathway or the gene set, so if we look at the diagonal Hotelling, so we know given if this is a diagonal, so we know the diagonal take inverse, it's once again diagonal. So it's actually in terms of the summation for based on each gene set. So exactly you are right. So up to the here, right? So the diagonal case, even for the two sample case, so we have this one. So we probably as you we have the same motivation. So we say based on the simulation part, so we do observe some good thing about the diagonal case, but the diagonal itself may not be perfect. So we may able to further improve. So that's the motivation. So that's in terms of motivation. And the one typical motivation is from the here. So if we assume the sample size, say it's very small, 2 or 3 or 4, and given you need to estimate thousands or maybe not that much, but estimate the many variance. So let's assume if for certain chance, if the one sample variance is very close to 0.0000 something. And after we take the inverse, so the one term will be hugely large, and in the summation part, it may dominate everything else. So we just wonder whether there are some way to further improve the sample variance part, and then given for the sample variance not reliable. So if we take the literature starting from the Tiejun, they the Stanford they the work, they simply add a small positive constant to protect from the very extremely small denominator at 0, and they have the Bayesian framework. They have the different ways. And also during my very early days, in my starting from my PhD study, I'm once again trying to develop in terms of the optimal shrinkage variance. So our first work, when I mentioned I have another new PhD student coming in. So our first talk, it's very applied. So we just wonder, in case like if the sample variance in the denominator is not stable, and in case if like the one variance is extremely small and dominate everything else. So we try to, provide some improved like the variance estimation. And then we starting from the here, so we trying to build, and eventually we come up with some like at least in practice very nice result. But it's like the main purpose for like today. I'm not going to like talk more about this study. Would rather to like trying to take like a closer look at the diagonal case. So so now like if like we follow like the previous slides, and we know, so for the so here like for our paper, so we present like both one sample and two sample, but like the next slides I only illustrate use the one sample comparison. So let's assume we have one sample case, and then like the testing problem, so we trying to take like a mean vector equal to like a pre-specified like the mean vector. And we know like based on the Hotelling for one sample test, so we have this situation. And for the previous like the diagonal Hotelling test, they feel like assume here it's the diagonal covariance matrix, and then like they simply like plug in with the diagonal case, and in that way it turned out this is simply a summation of like some like the one like the like in the gene level like the test statistics. So, and we know like in statistics, so we instead to like directly like plug in. So we have some like the very nice things, and if like we know something about statistics, we know like all of us know like the very like in terms of the test, we very standard, very common approach. We starting from the likelihood ratio test. So now we are actually take a close look. Okay, so now we back to your question. Assume the sigma is diagonal. That we assume. Though eventually when we trying to establish the null distribution, we did not apply it. But let's assume at the point the covariance matrix is diagonal. So then let's look into the likelihood ratio test. And then we trying to follow this one. And then we know like for the asymptotic case, so we often like take the log transformation and timed by -2, and we know this situation like in the very classical statistics, so we follow like asymptotically chi-square. So after we apply the likelihood ratio test, assume this is a diagonal, then we end up to this situation. And at this point, we then feel like the things are quite interesting. If we look back.
Sorry, wait a minute. No power.
Oh, no power? But my voice is large enough, right? No, them.
I think you can continue.
Okay, great. Okay, so we if we look into the like the Hotelling test, we know like based on the sample covariance matrix, and if we assume this is diagonal, so the diagonal Hotelling approach, they simply like for this one, they only estimate the diagonal entries with the sample variance. Okay, thank you. Yeah, these ones. Okay, so and then this one will end up with square divided by this one. But if we apply the very classical, we know like the likelihood ratio test has many nice properties. So if we approach to this one, then we can say, if we look into this up to like the certain scale n divided by n minus 1, and if we look into the second part, this is actually, if we take the summation for this part, this is something called diagonal Hotelling test. But now, with the likelihood ratio version, we are actually in the scale of log 1 plus something. So each component in pathway, we say like they are like a small number. Given like for like each component, this term is not that large, because that's why we need to take the summation, right? So if this is small and we apply the first Taylor, we know like the log 1 plus x will about x. So with a very like the interesting special case, if we simply like apply this approximation, we are actually our likelihood ratio version will exactly back to the diagonal Hotelling. So that's the interesting part. And we feel if even under the assumption the covariance matrix is diagonal, we should apply the log version, but not simply directly in. And so then when we trying to write the paper, so we hope to convince the referee or readers why the new test has some good things. So then I explained in here. In the log scale, so we expect the test ticket will be less likely dominated by some individual component. Given if this is one component extremely small, so then one term will go to really say million, billions, much larger, and they will dominate others. But in the log scale, even one term is extremely large. After we take a log, so then not that dominates. And in terms of eventually, so we are able to trying to build a more dense or say a very more stable now distribution, more robust now distribution. We are able to. And the second, the things given now we are a summation for the log version. So we first for each component we assume for this one. We try the test statistics with purely a summation for the UI. So then for UI we have certain results. And then for these slides, so we know despite this is simply additive version for the U, right? In terms of the log transformation, our derivation on the limiting or the null distribution. So we do count for the dependent structure among them. So this is just we start a point to find certain test statistics we can work on. So and then we have a result. So even so we have the certain for the covariance, we need a certain assumption. So this assumption we mostly likely from the literature. So not strong at all. I would say quite standard. And even for the U we follow the one the JASA paper in 2015 in terms of we need to satisfy some strong mixing condition or these ones. And this is the three paper I mentioned today. So this is another my PhD students. So work on this one. So the paper is just recently accepted. So we have some even nice the new project related to this area. But the paper is still writing. So we today so I'm hoping to report you later. Thank you very much.